All right, so welcome everybody. So tonight we're going to talk a little bit about Genie 3 was actually the original goal of the topic. Um, I rolled back to the first iterations of Genie and then tried to look kind of at the releases and how those changed. So the good news is that Genie, the first paper, was released as a paper, and there's a fair amount of technical detail on there that we could dive into. The bad news is the subsequent releases have been more blog centric and more kind of capability oriented and not technical details. So we can see
Hmm.
a little bit about what you can do, but very little insight into how they're doing it. But I was a little disappointed in that journey, but we'll make the best of it. So, okay, so here is the release. So Genie is this world model family from DeepMind, and it is uh, they have a concept that they call world model, and we'll talk a little bit about how it is. I envisioned world model as being a little more, I don't know, directed or something like that. Um, but basically, they model transitions from one image to the next, and in a way that maintains persistence, et cetera, et cetera. So we'll look through that. Most of that's covered in this first paper. What's that? February 24. Um, and we'll look through the detail of the architecture then. And then there's been two releases since then. The August 5th is the most recent one, where they're getting some pretty nice resolution. And most importantly, this is now in Genie 3 is getting to where it's real time. So it's actually generating these models on the fly for you, and you get to interact with them. So that'll be the plan. Okay.
It's cool.
All right. Let's see. You know what I didn't do? Well, when I get to the first video, I probably will have to reshare because I forgot to do the optimized stuff. Um, actually, I haven't. Have I started sharing?
No,
No,
I
I
haven't.
was I was
No.
about to.
You
Okay,
and me,
here we
Ted, are
go.
on the same line. Like,
Okay, that's why it looks. Okay,
now you're
okay.
sharing.
Now I'm sharing. Okay, this is this the slide I've been talking to then. Um, so I can move these out of the way. So yeah, so again, 2024, Feb 24 was the first iteration with a paper. December 24, they had another one. I think there's a little bit of inference about architectural changes there, but no paper release. And then August 25 is this most recent release that's kind of exciting and looks cool. Um, this was a summary of the difference between them. This was done by Gemini, so take it for what it's worth. But in Genie 1, they do an autoregressive fit to these basically video games. They're watching video games and trying to understand what drives the transition from one image to the next. In Genie 2, they switched, as far as I can tell, the only technical switch was here they were using a MaskGIT for the generative side, the decoder, and here they went, I think, to diffusion. And then I don't have any insights into Genie 3 architecture. The games that they were simulating in Genie 1 were from a platform that does 2D games. So it's just, little 2D characters running on around a 2D world. Whereas in Genie 2, they started modeling 3D. So it's not that they're presenting 3D, they're still generating 2D images, but the world that they're modeling uh, is a 3D type of world. Um, and in Genie 3, I guess they're claiming that it's still 3D, but you have a little bit more control over viewpoint. The output resolution of the first version was really pretty small. They upped it in Genie 2 to 720, and in Genie 3 retained the 720p. Controllability in these first two versions, it wasn't really real time. It was actions that they learned. Um, they inferred action, latent action. Whereas in Genie 3, they've switched over now to where it's during playback, they will allow you to interact with it. And it's generated quick enough that you can interact real time. Yeah, go ahead, Ted.
Are you going to dig into this latent action business? Because it's a
A
little
little bit.
confusing.
I was a little confused. Why we can go. Well, I have a slide on that, so we'll dive in a little bit what they were doing. The exactly how it works, I wasn't quite grokking it, but yeah, we will look at that.
Thanks.
Let's see, anything else? Persistence. The biggest thing that they talk about is it moves from kind of, I think it was a minute and a half or a second and a half or something like that out to multiple minutes.
Hey,
Now, or
Roger.
no, it's 16 seconds out to multiple. Yeah.
Roger, on your slide it says Gemini. Is that correct?
Oh, I just asked Gemini to summarize the difference between the
Oh, I
models.
see. Okay.
Sorry, that's what I meant by it. That's why I'm saying, that we probably should fact check Gemini, but they're all in the same company, so it's their
Okay.
fault. It's on them. Um, yeah, and then they had very small ones for the original. I guess that was just kind of researchy. And then Genie 2 was up at 11B. They moved it up to, which is funny because with language models now, for a while, we were doing a lot of like AI things, generative AI. And since then, since switching over to the language models, this parameter counts have become so big. An 11B parameter count seems pretty small these days, but that's what they were using for that. Okay, so here's the idea for Genie, the original. They would take, and these are the types of 2D worlds that they played in. I forget what they call it, as platform or something like that. It's just a place where people generate 3D, or excuse me, 2D games, and users come in and play it. Um, so they would start with, I believe in all cases, some sort of image. So I guess you could generate an image from a prompt using something else. You could hand draw, you could take a real world photo or whatever. You'd run it through a Genie, and then um, this would generate essentially the sequence. It'd kind of take that initial image and say, oh, well, if you were playing that, how would you play it? And you'd have a limited number of controls. So the controls are, I think, discrete controls because uh, they're coded, or quantized. So it's not a continuous thing. So it equates most closely to like, an A, B button type of thing, left, right, up, down, whatever. In fact, they call that out there. And then it allows the image from this original, well, what would happen in this video game? And it imagines what would happen. The character moves right or jumps or whatever. And that's kind of how you would, I guess this is the inference side of this Genie model. Um, so I've got the paper, but I'll pull out just a few of the figures that were kind of most useful. We can roll through the paper if we want to dig a little deeper. But so the training, basically, they're taking these sets of various number, depending on the model that you're training, of images. And the first thing is to just take a VQ VAE. Yeah, VQ VAE. And Ted, you might know these better, but I think this is like a VAE. So it's an autoencoder, meaning that you take an input, you run it through something that kind of compresses it down to a smaller representation. That's called the encoder, and then you expand it using a decoder back up to the other, and then use some sort of loss between the input and the output. And that's how you train it. You're just looking for, I want to regenerate the input, but do it through a compressed representation. The VQ is vector quantized, I believe it is. So rather than this in a VAE, where this would be a few parameters that represent a distribution of particular dimensions, instead you're compressing that down into a set of code words, and that you can kind of control what that code word is. So it's a discrete, and the result is discrete. The encoder will spit out a set of discrete tokens, and then the decoder will take the discrete tokens and regenerate an image. Is anything, Ted, did I miss anything on that VQ, VAE?
Um, yeah, so the main thing is instead of a VAE that has a continuous representation, you have a discrete representation, which is a good fit for anything that's using an LLM, because LLMs have a discrete fixed vocabulary. I don't remember whether or not Genie 1 actually used a simple VQVAE, but a lot of models more recent than the original VQVAE, if they want really high precision, actually what they do is, I think the term is residual vector quantization. Um,
Mm.
and so this is what's typically done in audio, where you quantize it, so you're rounding it to the nearest vector, okay? But then you calculate the residual, and then you run that through a vector quantization. And so for like audio, it's common to do that 4 times. And my impression, Julius, correct me if I'm wrong, but that the first one will tend to get these large low frequency elements, and that as you go, you're getting higher frequency elements on those residuals.
Yeah, and I've seen up to 9 layers of,
Wow.
I think the Descript audio codec, when I looked at it, was 9 layers.
Yeah. Okay. Yeah, I don't think images tend to have as much dynamic range on the frequencies, and so they don't necessarily do as many. But that is something that you can do. Is you can run the residuals through um, more than once, uh, and thereby get higher precision. And if you have a fixed number of times you run it through, you can either concatenate those, or you can just say that every whatever image corresponds to multiple input tokens to your transformer, and then assuming you always have some sort of positional encoding, if you do that, then let's say you do it 4 times, then you basically know that like token 5 is really just the beginning of 4 tokens of the next image, so to speak. Okay. So just depending
Yeah.
on what
Yeah.
your model dimension is, you can either stack them and have something that's much, higher dimension, and then you only need 1 token position for each, or you can just say I'll allocate length. So either length or depth, either way. But that's a way if you're just needing higher precision. So the original one, that was whatever you said was like an Atari game, like 200 by 90 or something. That was probably
Yeah.
just simple
Very small.
simple
Yeah.
VQVAE. But if you're
Yeah.
doing 720p, then maybe they're actually doing this RVQ variant to get higher resolution.
Yeah, it wasn't clear again because they didn't have a paper or anything, but they did. I think it was mentioning that it was doing upscaling. So I think this eventually got up to a 360 by something, I think. And I think I read this to be with upscaling meant that they had a layer that did upscaling after the decoder,
Yeah,
but
yeah,
not sure.
that'll be on the side, but on the input side, you still probably have higher resolution. That
Mm,
you
okay.
might downscale a little, but if you're getting more data in, then likely it's using this residual vector quantization. The main thing is exactly what you said. It's switching
Okay.
from continuous to a discrete space.
And then
Um,
back from discrete
and
back up to.
and this is going to be more effective than like just using a linear embedding, because right, so like the way we embed words tokens is you just run it through a simple linear layer, but that's limited to a linear embedding, whereas vector quantization can be a very non-linear embedding.
Yeah,
Gotcha.
I've seen it many times now as kind of the standard continuous to token converter. You have some continuous stream like, image, video, or audio. And what you need to do is bring it up to the vocabulary level. And so it tends to go through some sort of dilated convolution until you get to the information quantum that you need. And then you vector quantize, encode that. And that's your vocabulary. And those vectors should mean something reasonable, like it should be like a phoneme, or at least part of a phoneme in speech. And you're a fragment of a word, word to vec gives you a substantial fragment of a word, or at least a syllable. So that seems to be the basic idea is to go from this continuous stream of, not very informative per bit information and bring it up to that level that really means something, but not more. These are your atomic primitives at the bottom. This is your vocabulary. And so you go through a customized code book from the continuous representation to an aggregated, sampled sequence of tokens in the vocabulary. That's a very fundamental conversion stage that I've seen everywhere, it seems like, by now.
Okay. So the other thing that they talked about in their architecture quite a bit was this spatial temporal transformer architecture. I think it's spatial
Hey,
temporal blocks.
hey, Roger, can I add one more thing?
Yeah.
This is very interesting. We were trying to make the VQVAE go away because it's hard to train. It's got
Okay.
its own losses and it's very difficult to get the vectors to uniformly distribute throughout the space. They'll easily get bunched up and there's just a pain. And so then there was this thing that came out from Google, I think, called finite state quantization, FSQ. But it's really a very simple idea where you just do hypercube sampling. So you just instead of learning the code book, you just decide it's going to be a uniform grid in this hypercube or rectangle, and you just assign the symbols that way, but at the right level. You still have your like dilated convolutions that get you to the high level that you want to be, the phoneme level or whatever. And then you just burden the downstream transformer with dealing with that and just, letting it work with those codes. And if it wants to evolve some better um, quantization, if it wants to work on them further, it can. And that's been shown to work. And that was what the paper showed. And so in
Hmm.
audio, they tried this, and one of our authors' name was Julian Parker, and I don't remember the others, but they tried this for audio, and it worked, but the transformer had to be a lot bigger. So it's a lot bigger. So let's say an order of magnitude bigger. And so I'm just vaguely, it was very significantly bigger. And so you can find the details on that, but that's the payoff is that by doing the customized vector quantization, you're able to greatly reduce the size of the downstream transformer that's going to work with this vocabulary. So that was a very important result. I thought I would throw in there.
Yeah, I'm glad the story kind of ended up that way because my intuition was that it kind of the embedding space, in this case the quantization, I guess, um, there's a lot of magic that happens there. It's kind of amazing what falls out when you get the embedding. And so yeah, just randomly assigning it does seem like you'd have a lot of work to do afterwards then to correct that. So,
And you can do it, but at a high cost.
right, right. Okay. Let's see what else. So the spatial temporal transformer architecture. So what is this? So basically the idea is that at each timestamp you have attention, you pay attention within the other cells. These follow the VIT, which I didn't grab the VIT paper, but basically, if I recall, they divide an image up into a bunch of cells, 16 by 16 or something like that, and then they come up with an embedding for each of the cells within the image. And so this spatial temporal transformer, what they do is they will, at one layer, have an attention that is constrained to that point in time, that frame. And you can attend to other cells within that frame. And then they will have a separate layer where instead of attending kind of spatially, you attend to that same cell in all of the images in this, the stack of images that are coming into the input. And then they layer the standard feed forward layer on top of that. And that becomes the block that then gets repeated multiple times. So it's a little different than you have in a language model where you have one attention layer and then one feed forward layer. In this case, you have one that's within image, and then the other's the same position in the image, but through time. And I think we'd seen some CNN type architectures that had optimized that way. Kind of naively, you would just attend to every cell in every image in the stack, and let all the attention figure it out. This computationally is much easier, and then by layering them, you can get the right blend of attending to neighboring cells versus attending to earlier cells. Does that make sense? Okay. So
Yeah,
that they used. Go ahead.
so Roger, the key thing is that the alternative to this would be naive attention.
Yep.
Okay. And so here they've drawn it very small, where there's only 9 tokens per frame. Okay.
Yep.
But if you had 100 frames, then every token could attend to 899 other things, and that's a very expensive attention calculation. But the
Yep.
spatial one, you're always attending to yourself and 8 other tokens, and that's it. So it's very cheap computation. And then the temporal one, it is still going to be as many frames, video frames, as you have. It can attend to all of them, unless they cap it with a window. But so you can see how the cost of attention is quadratic in the number of things you can attend to. And so it's way better to attend to 30 things, 9 things, than 300 things.
So this one was used, I think, for each of the 3 elements. I think they were using this spatial transformer. And they referenced prior work that had not done that optimization. And like you said, Ted, computationally it was much more expensive. So this had appeal and good results. So okay, so let's see. So the first part then is we get this tokenizer that we built training one of these VQVAEs, the encoder decoder. So we use the encoder to create the tokenized input stream, and then they run it through a dynamic model. So the dynamic model basically takes a look at not just the most recent image, actually. They feed it the entire time series, I believe. And they also feed it, let's pretend we knew what the action was. Now we don't, and we'll talk about how they kind of fill that in, but let's pretend we had access to the action between each one of these frames in these games. So the image of the game, the action, the image of the game, the action, et cetera, that whole stack then gets fed into a dynamic model, and the dynamic model then will predict, okay, what's the next token, or excuse me, the next, well, it is tokens actually. It'll predict in token space what will represent the next image, and then they decode that to generate the image. So this dynamic model represents kind of how does the image progress in time. So things like momentum and gravity and stuff like that end up embedding somehow into this dynamic model. And then these actions, it learns what those actions do to the image, where maybe it moves the character to the right, or maybe the character jumps, or maybe the image pans to the right or pans to the left or whatever. It learns all of that in this dynamics model. So that's the general workflow. For some reason, this image, this came out of the paper, but they don't show it, but there should be, I believe, this being the encoder, there should have been a decoder right there before the output frames. Does that make sense? Any questions on that? Okay. Let's see. So the other part, and Ted, this is the one that you mentioned early on, is the image, the video. So they had the statistics for later, but I think they had like 30,000 hours worth of video game recordings that they were training on. And in those, it had the video output of the game, but it didn't have anything about, what was the user controlling. It was just recording, some user was doing something, and it was recording the output images. And so they need this because the user action is one of the things that affects next state. In order to train this dynamic model, you need to know kind of not only what is the model been doing, what's the latent representation, what has it been doing, but also what actions are taking place so it knows how to predict the next frame. So we need to find this action, but it wasn't there. So what they did is they came up with an unsupervised learning mechanism that would take the images and would predict what was the action that occurred before the T+1 or the next image. And this is the one where, okay, so one thing, again, this is a quantized action. In the case, they played with different numbers, but they limited it to 8. This will eventually correspond to things like, the A, B, X, Y button, that type of thing. So they limited that. This training mechanism, they did a comparison. The two things would be is that the loss function is the difference between what they predicted the next token would, or the next image would be versus what the ground truth was. And the other thing that was kind of interesting is they talked about it over here, I think, is that they actually ended up training this guy in pixel space, not in latent space, which was kind of handy. They kind of surmised that, well, maybe there was something during the quantization that got lost, which I struggle with a little bit what that means, because they are quantizing for the rest of the system. But anyhow, this is the model that they used for training the AT. And I don't know that I can provide, Ted, this is the part that you were asking the question about, like, how does this make sense? How does this work?
Yeah, I think basically the way I think about it is now remember, these are platformer video games, okay, that they have screen grab recordings of people playing the video game. But what they don't have is they don't have labels of what the user's doing on their controller in terms of the joystick and the X button and the A button and that kind of stuff. So if you were given those frames, up through time t, so you're given the first 100 frames of someone to play this game, and let's say there's the ability to jump and there's the ability to duck, right? If you are trying to predict what's going to happen in the next frame, and your latent space is down to like 8 possible actions or whatever, then you're going to have the lowest loss prediction if you actually, in your latent space, have something that encodes the idea of jump or something that encodes the idea of duck. And if the only thing you had was, I don't know, punch or kick, because like that's you're thinking from like some completely different video game or whatever, right? Then you're going to do a terrible job predicting the next frame when the character's like going up and jumping over something. So ultimately, the latent model has to, in order to have low loss, has to learn the actual actions that the users are able to take. And if you don't need user actions, like if you have gravity or something like that, then you're wasting part of your space, predicting something going off the edge and going down, right? Because you don't actually have to hit a button for that to happen. It just always happens every time you go over an edge. So I think it sort of makes sense, but they never quite said it explicitly. And so it seems to me that if you had a video game, then if this model learns well, it knows that there is some button for jump and some button for duck, but they might call Y the duck button and they might call A the jump button. But in fact, that's completely wrong. A was the duck button and B was the jump button. And so they don't necessarily know which button on your controller was the one you pressed. They just know that there is a button. And so then I didn't see in the paper, maybe I didn't look closely enough, but so then when the model's fully trained and they let a user interact with the world, you need to figure out what button is the jump button because nobody's telling you, so to speak. That
Yeah.
makes sense?
Yeah, it does. The using it is fairly straightforward. The one I was struggling a little bit with is, so this somehow these encoder decoder is going to have to focus kind of on the things that the user affects, that the action affects, and ignore, because it's predicting the next frame, right? So um, it's going to get a lot of noise. It doesn't need to learn gravity. So it's going to get a lot of noise in that signal from gravity and zooming in and zooming out and stuff like that. But presumably it learns to focus on, the character moves up and down, or the character moves forward or something,
Yeah.
left to right, or pans left, pans right type of thing. Um, so yeah, it's interesting that it is a next frame predictor, but it focuses on attention.
It focuses on the action. Yeah, yeah. So no,
Oh, excuse me, focus on action. Yeah.
if it's a big enough model, it can predict what would happen in the next frame if the user takes no actions.
Yeah.
And in that case, it could get fairly low loss a lot of the time, right? But then it's going to have higher loss at key points, and that's where it can use its latent model to say, oh, I'm guessing the user did something here because my prediction was off by quite a bit. The user sprite ended up moving up, a couple pixels, and I was expecting it just to go to the right.
Yeah. So the interesting thing is ultimately then, so this is just kind of backfilling for the fact that on this unlabeled data that they've collected, just the videos, they don't know what the action is. Once it's used for training, they just throw this stuff away. This is just to get this label for these actions.
Yeah.
So.
Yeah. And I can't remember, there was some other thing I saw where it was like Minecraft or something, and they actually went the other way. They got a bunch of people to play, and they actually recorded all of the actions or whatever, right?
Interesting.
So
Yeah.
if you can get that data, great. But most of the time you don't have it, and so that's why.
And they were able to. Yeah.
You can get a lot more training data if you are willing to just accept any screen recording.
Yep. Okay, so this was when they were trading their encoder decoder, picture of that. And the dynamics model then, once this is trained, it takes these internal latent space, the full series of those. The dynamic model will generate the next time step. It also takes the whole series of the actions up to that point as well. And then when you're actually doing, when you're actually doing inference, you're just looping through this, adding an action at a time. In the case of Genie 1, these actions would have been ones that would have been like, it wasn't interactive, so they would have been pre-recorded what they were going to do. Later on in Genie 3, they actually become the live user actions. So initial starting image, generate a latent space, dynamic model, and an action. Dynamic model generates the next latent space, put that back in, feed that back, generate the next one, et cetera, iterate multiple times on the output side, taking the latent space and generating images. Fairly straightforward. Let's see, some of the highlights in the paper. Yeah, there's 200,000 hours. Somehow they called it down to 30,000. I think they used some sort of machine learning technique to do that, I remember. And what was I forget the name of the platform. What'd you call it, Ted? The gaming
Platformer games, you mean?
Platformer, yeah. I hadn't heard of it before.
Oh, yeah. If you play video games, I mean, it's like, Donkey Kong or whatever, where it's just 2D and maybe side scrolling, but there's no 3D perspective.
Yeah. They did say that they also added this RT1 data set is some image recording from robotics videos. They added that in to test like how well does it generalize to it, blah blah, and the parameter sizes that they created. So that was the highlights, I think oh, right, here was one of the other ones. So another term our technology they referenced was this MaskGIT, Mask Generative Image Transformer. So this one, naively, if you are, I think the original VIT, was just scanning the cells within the image kind of linearly like this, where you just kind of raster down from the top all the way down. In this paper, this MaskGIT, it's more of a hierarchical one where they will, at each point, so it iterates multiple time steps. So here you're generating just one next cell each time, and so you're iterating 255 times. In this case, they're doing some sort of random, from what I could gather, random selection of what cells to generate. They generate one, and then next time they generate multiple, and next time they generate multiple more, and they're kind of in parallel, filling in the parts of the image. So it's just a quicker way to generate it, but it is a generative. It's not. I don't think it's a diffusion like in this case. It's a generative model directly. So there's the paper if you want to look at that any further.
Yeah, so VIT was the vision transformer, and it was only an encoder, right? So the first thing they did was they did like classification on ImageNet using a VIT.
Oh, VIT was only encoder side. Okay.
Yeah. And so how do you turn it into a generative model? Well, VIT does patches, right? If you remember the VIT paper, the subtitle was something like a patch is worth an image is worth 16 by 16 patches or something. I don't know, something like that.
Yeah.
So it's breaking it up into these patches. So what you could do is you could just build a transformer to predict each of the patches from a VIT, and then turn it back into VIT never turned it back into pixels, but the process of converting from pixels to a token patch was like a linear layer. So it's not like something super complex. You can reverse that, right? And you could do that auto-regressively start in the upper left corner, and then the two problems you have are it's slow, and you have this dependency where pixels towards the bottom of the image are aware of what was above them, but you can't have the reverse where pixels at the top of the image are aware of what's below them. So MaskGIT was an earlier paper where they, BERT style, they would just sort of mask out pixels and ask the model to predict what was missing. And then once you can do that, then you can use it as a generative model where you start with nothing and you slowly add pixels. And one of the things that I think generally if I remember right, MaskGIT and these other models, what they did was they would, as you said, randomly pick pixels and they'd fill them in, and they're being informed by the pixels that you already have. But
right.
Most of those models never modified a patch. I said pixel before, a patch, once it had been picked. So, it looks like in the second image, like you've picked this patch that's about in the center, left, right, and near the top. And then once that gets hard-coded, then everything else sort of fills in around it in a way that makes sense. Okay. So that's like a picking all the different pixels, sampling, without replacement. But an interesting thing would be if you sampled with replacement, then there's the chance that that pixel gets updated even after it got picked. Now that other things have been picked, you might want to tweak a little bit what you originally decided. And so then that starts to look a lot more like a diffusion process,
Like inference time thinking, it looks like, iterative, going over what you just came out with and maybe changing your mind,
Right.
Yeah.
Yeah.
So then there's the VAR paper from December this year. I don't know if Google's using that, where they said, let's start with a low res image and then we'll gradually go higher, other way, higher and higher resolution. And then that's a way that has very few steps, but very clear conditional relationships.
And the
Right.
XAR paper that was right after that did the same thing, but it did it with not random subsets, but well, just general subsets. So they could be
Right.
random,
Yeah.
but it was, that kind of generalization to what you see here. So this looks like XAR.
But we don't actually have any details. It's all proprietary what they did in Genie 2 and Genie 3. So we really don't know.
Right.
But so that would be if it's autoregressive, it could be something like that VAR paper, or it could be a diffusion model. Either way, the idea is that you don't generate in one step, and that each step is informed by all the information you have from the prior steps. In autoregressive, it's literally, right, you just give it the previous and you say what's the next. And in diffusion, you're learning, right, that score function in order to know like what direction to pull things as you go from one time step to the next.
So what was the one where you start at low resolution and you get higher and higher resolution? What was that?
They called it VAR, visual autoregressive modeling.
Okay. And when did that one come out?
I'm pretty sure it was December. Well, it must have been a little earlier. It won one of the best paper awards at NeurIPS in this past December.
It was also
Okay.
number one of the benchmarks until XAR came along and dislodged it. So I think that was on ImageNet.
Yeah.
Okay.
So
these guys wouldn't have known about that at that time then. The VAR.
Well, not in the February, but in Genie 2, it's possible they knew about it.
Yeah, this is Genie 1, right? We don't know
Yeah.
what happens in Genie 2.
Yep.
So
Sorry.
this is kind of Ted, you pretty much summarized all this. So they're just masking it, filling it in, and that's how they learn. Okay, so again, what happened is, so in Genie 1, they had this announcement, and this was the paper. And we've gone through most of the important things here, unless you guys want to dive into any deeper details. They did provide some things like some of the training information, model size, stuff like that. They did some ablation studies. There is more information about the models, I think, down lower, where they talked about details like encoders information, sizes, etc., all using that spatial temporal transformer.
Totally random, but Roger, did you notice there's little images in the lower right corner of every page?
I did. I didn't ever try to flip through and see what they did, though.
Yeah. I think it's a flip book if you.
Yeah, probably. Anyhow, so this one, yeah, fairly well documented what they did. I don't know if you could completely recreate it from this, but a lot of things that are get you in that direction. And then Genie 2, as best I can tell, this is the only thing that came out. So they did it in the form of a blog. And you can see that they've now transitioned to these 3D worlds. And again, kind of this, whatever the 8 actions are, navigating it. So this video right here on, I think this was the main one that they did that kind of covered it. So this is well, you can just see what it says. So generating a single image then from that prompt, and then these worlds become playable from there in kind of a classic first person. Well, I guess not first person, but first person is one of the modes that it can operate in. And they didn't really go into too many, like I said, they had a lot of examples, kind of this is what we're doing, some ideas about how to use it. but again, not much more detail. They talk about this long horizon memory, but don't describe how that is done. Now, it looked to me like it might have been something that it just kind of emerged, that it's, when you have this spatial temporal transformer model, that you end up, that attention gives you some sort of long-term memory. I was kind of thinking hoping it might have been like some sort of, agent they used or something like that for memory, but it didn't look like it. So again, we're talking mostly features. Anybody, any questions or comments that come up, just feel free to jump in. I'm going to just kind of flip through their examples. Again, it ends up being kind of a demo thing more than anything. All of these are being generated directly from their latent one image, and then advancing the latent state, latent representation using the dynamics model. And here's some of them that's beyond just moving. It looks like, it looks like some of these, the image quality is pretty low. And if you look at what's happening to the characters and whatnot in the background, they're fuzzy. So it's interesting that it's working in latent space, advancing in latent space. And I like that, but it's still at a level where the quality of the image is not that high. Physics, somehow the dynamics model is learning something about physics. I guess gravity is kind of a physics.
I wonder if it's learning like Mario type physics where like you can double jump in midair.
Yeah. I was thinking about it, they're saying it's learning physics, but it's Mario physics, right?
What, you can't do that, Ted?
I have tried and the double jump has never worked for me in real life.
Yeah, I guess
Does
Reggie's
it,
a bit, and then I can
it
pull
doesn't
out.
work for me on the controller just because I have zero hand-eye coordination, so don't feel bad.
If you remember the what was it? The Hobbit movies or whatever, there's one where the bridge is falling and Legolas is so fast that he's able to like run up on falling stones that are not supported, they're just in midair, but he's so fast.
Yeah. And so light on his feet too, right?
In fairness, I guess it's learning Mario physics because that's all it's seen. So if you had, videos of real world, presumably it learned real world physics.
Yeah, like I don't sail, but I'm assuming that boats don't turn the way that boat turned in the video. Like that's the way boats turn in a video game. That's not the way they turn in actual life.
Yeah.
Has
And when
it-
you get into the real world, that it's not an 8-dimensional action. There's lots of things that would affect the next image.
Has anyone ever seen multiple resolution? I mean, can you imagine doing all of this in a kind of wireframe mode where, you can have enormous amounts of memory because it's, very sparse. This is the way computer graphics evolved, right? So they did things in wireframe right up to the very end, and then you run your rendering, and it could take days, and they've been doing it at like Pixar and all the major, computer graphics world. I mean, why not do it that way for these models? You just have the whole model just be in this sort of wireframe mode where it has incredible memory and object permanence, because you just hang on to all that, and then just render it on the fly in kind of a separate pipe. It's like a downstream, separate system. Has anything like that happened? It must have.
You're kind of jumping ahead to. I had a similar question, and that is that instead of what's the advantage of like storing this in some sort of latent representation and having a transformer that attends to whatever the appropriate part of the history is. What's the advantage of that versus instead, we've already got 3D rendering packages that are pretty efficient, especially if you start throwing the type of GPUs we throw at language models. What if the AI was instead driving the 3D representation, whatever the model is, like a Unity engine, game engine, or something like that? If it created the objects in that world and then it animated the objects in the world, does it end up getting better performance and better permanence, et cetera, et cetera?
So I think you can argue that it's doing a slight amount of that if it's thinking in latent space and requires super resolution to fill in the details. But to your
Yeah,
point, Julius, you could certainly be more extreme in terms of like, thinking in the wireframe world.
you're thinking actually thinking in like learning the dynamics in the wireframe. Is that what you were saying, Julius?
Well, yeah, but you could go further. You could have dynamics implemented, kind of hard coded in the external world. I'm actually thinking of an analogy of the real world, right? So it's like we're LLMs, and we live in this world where there's object permanence. How is that implemented? Well, it's certainly not in our brains. So we're able to reason about things and manipulate things, but we're in this world of constraints because that's all, it's going to obey the laws of physics. So you could have this physics environment where the laws shall hold, and then the LLM just kind of flails around in that like we do. I don't know. It's
Right.
like a useful analogy. And it's analogous also to the wireframe distinction. So you have final rendering versus wireframe. Um, yeah, so those are really separate, but
So that's where Ted and I talked about this briefly beforehand, and I had raised that question of more of a hybrid type of solution. This was a TED talk that somebody did where it's a little bit of a kludgy example, but he basically is giving prompts to language model. Then language model is then generating the code. I think it was in a Unity environment that renders that creates the 3D world and gives it actions, behaviors, etc. And then you can interact in that. So the physics are implemented by the Unity engine, um, and
perfect.
the creation of the objects in the Unity world is this language over here is code that was generated by a language model. I kind of like that. I don't know what the pluses and minuses are. I don't know if anybody else has opinions about it, but it's another way. It depends what your end goal is, but
Yeah.
if you're trying to create rich 3D immersive environments, um, a language model or something like that, transformer-based something or other that's controlling a physics and rendering engine seems like a viable option.
Yeah, give it a tool. LLMs are so great when they have tools, right?
Yeah,
And they're
yeah,
good at them. They're good at manipulating tools. They're not good at being reality.
yeah. I guess in this context, it's not really the language model that's in Genie. It's not the language model that is doing this. It's this trained dynamics model.
Mhm.
But there's a lot. I don't know. It just seems like I don't know what the mapping is from latent diffusion to dynamics in the latent diffusion and the latent diffusion or the latent diffusing into the image. I don't know how much compute it is. I guess I'm kind of inferring that that's a lot more work than just what a Unity engine does.
Mhm.
Anyhow, did we kind of finished, I think. Oh, this was one other point. In this Genie 2, they allow you so they created this image and then they were able to use text prompt to drive it to whatever the next step to guide the dynamics model using text prompts. I remember those games when I used to, you'd have something like this and it'd just be text only and it described the room that you just stepped into. Remember that? That stuff is quite a bit more advanced. Okay. This was all we got, I think. It's an autoregressive latent diffusion model. So we know it's diffusion. They switched to diffusion for some reason. I guess
So it sounds like they used diffusion to render the frame,
yeah,
and they used a transformer to tell the diffusion how this frame should differ from the previous one.
yeah. So transformer, the spatial temporal transformer is the dynamics model, generates the next latent representation. And yeah, then this decoder becomes a diffusion from that latent representation, is what
Yeah.
I understood.
I mean, I'm anthropomorphizing a little bit, but it's like last frame, except Mario's a little bit further to the right, and the whatever bad guy is, a little bit lower.
Yeah, yeah.
I don't think that's literally how it's represented, but I'm saying that the dynamics has to say like I've seen these previous frames, generate something very similar to this
Right.
previous frame, but this is how I'm telling you it should be different. And then the diffusion model does the actual pixel rendering, so to speak.
And I think the decoder only works off the most recent latent, whereas the dynamics actually, in this case, they're not showing it. Yeah, they are because it accumulates. The dynamic model, the Genie that takes the prior states and the action, looks at all the states, not just the most recent state. So it's more like that attention that goes, attends to all history. But the decoder, I think, just takes the latent representation of the last state and diffuses that into an image.
Yeah, yeah. So actually, to take Julius's question very, very literally, they're giving the LLM a tool which is a diffusion um, image, frame generator. What they're not doing is letting that generator have some kind of world knowledge across frames. It's generating each frame kind of, from scratch, potentially conditioned on the previous frame, but as opposed to, having like a wireframe or having like just a something like that.
And isn't it well known for having really good memory? In other words, it's a new level of short-term memory of what's there, so that if you paint part of the wall and go away and come back, the same paint. I mean, doesn't it have superior memory? So it must be getting that from the diffusion generator somehow, I would imagine.
I think it's just long context LLM, right? Gemini has a
What?
million token context.
So you're saying it's in the transformer component that it would have this memory.
If it's still this architecture, there's no external storage, and so it's just
Right.
long context.
Yeah, they talk about it as kind of a unique feature, but it doesn't look, at least here, they're not describing it as a separate architecture.
Mm-hmm.
I've heard other references when we start talking about, agents, memory agents, where I assume, I haven't read up on them closely, but I assume that there are things like, put this away, save this in memory, go look up something similar to this. And I guess because they were talking about this long-term memory persistence as something unique, I was kind of expecting to find something like that. But yeah, it looks like it's more just you can attend to things that happened earlier in time, and therefore you get long-term memory.
I remember
Okay, so
when I was at Google I/O year before last talking to them about this, and they were talking about what a real focus on maintaining a long context on this. Maybe this is one of the reasons, or one of the results too.
yeah, yeah. Although again, remember, there's one layer where you're only tending to the current frame, and another
Mhm.
layer where you're only attending to that. I was calling it cell. What did you call it, Ted? The patch. You're only attending to that patch through time. So it avoids the quadratic already from that.
Hmm.
Okay. So this is the most recent one then. This is the one that came out 5th of August. And mostly it seems like it's richer and the memory lasts longer, so they can generate ones at 24 frames per second to a few minutes. Resolution is the same as prior. And one of the most important things from an experience perspective is that it is real time. It's rendered real time. So you get this 24 frames per second at 720 real time. And that means you can, it's more immersive. You can be in the world. I'm going to play this video, it's like 2 minutes. It's their introduction. Let me know if I don't have any video here, but if somebody can say something, make sure we're getting sound.
Sound is good.
What you're seeing are not games or
Is
videos.
that good?
Yeah.
Okay.
They're worlds. Each one of these is an interactive environment generated by Genie 3, a new frontier for world models. With Genie 3, you can use natural language to generate a variety of worlds and explore them interactively, all with a single text prompt. Let's see what it's like to spend some time in a world. Genie 3 has real-time interactivity, meaning that the environment reacts to your movements and actions. You're not walking through a pre-built simulation. Everything you see here is being generated live as you explore it. And Genie 3 has world memory. That's why environments like this one stay consistent. World memory even carries over into your actions. For example, when I'm painting on this wall, my actions persist. I can look away and generate other parts of the world. But when I look back, the actions I took are still there. And Genie 3 enables promptable events, so you can add new events into your world on the fly. Something like another person, or transportation, or even something totally unexpected. You can use Genie to explore real-world physics and movement, and all kinds of unique environments. You can generate worlds with distinct geographies, historical settings, fictional environments, and even other characters. We're excited to see how Genie 3 can be used for next-generation gaming and entertainment. And that's just the beginning. Worlds can help with embodied research, training robotic agents before working in the real world, or simulating dangerous scenarios for disaster preparedness and emergency training. World models can open new pathways for learning, agriculture, manufacturing, and more. We're excited to see how Genie 3's world simulation can benefit research around the world.
Okay, how'd that go? I know I think I have some bandwidth issues here, so hopefully if there's a little bit of breakup,
No.
that was probably my
It was
Not
great.
good. It was great. Yeah.
Okay. Okay. So yeah, that's I believe their official video introducing it. They talk about kind of the differences comparing to other things. This is one question came up with to me is like, okay, they got Genie and they got VO, and what's
Mhm.
that about? And I think it's really kind of exploring two different dimensions. Genie, the issue here is it's controllable and it's real time. That's kind of the focus. It seems somewhat overlapping with VO, but there's a video that I linked to.
VO strikes
Somewhere.
me more as just you prompting an environment or something like that. Like two people walking down the street, one person has a hat on, the wind comes up and it blows it off, that sort of thing, versus interacting with the environment.
Yeah. Yeah, but I don't know how much, but there's a lot that's behind
Well,
the
they're saying,
scenes, I would think, right?
yeah,
I mean,
but
if
they're
you're
saying right
generating,
there, notice the last two prompts here have to do with interaction. And VO, you really, the latency type thing, it really doesn't, it doesn't apply because it's prompted. You know what I mean?
Yeah.
So I think it's two products for two different, I don't know, two products, two toys, whatever you want to call it, for two different target audiences.
Hey, Roger?
Yeah.
For Genie 3, I looked at a few of the examples, but do they have any examples that are not first-person view?
Yeah, not sure. I don't think I can't think of one I saw. Well, I mean, this isn't exactly, this robot guy isn't exactly
Okay,
first
yeah.
person.
So that's the, I don't know what you call it, but the hovering camera.
Yeah, the
behind
over-the-shoulder thing, yeah.
Yeah. Okay. No, because I'm just thinking if you wanted to do something more VO-like, then you could. It looks like maybe you can prompt it like where the camera is supposed to be.
Mm-hmm.
Yeah, I think so. And they talked about that in the actually the Gemini summary. They talked about it that it was promptable. Yeah. Sorry, lost train of thought there.
Yeah. No, I mean it's just right. Like if you were doing just a vanilla Hollywood movie, right? Most of the time the camera is not first person. Right? Most of the time the camera is sort of on the outside, behind the fourth wall, looking into the scene.
Yeah.
Right.
And most of the examples for Genie 3 were not that. I guess they were showing off, like the ability to look around, but like, what if I actually don't want one way you're looking around? What if I actually want a third person view?
Yeah. Yeah. So Gemini summarized it as these 360 environments, which I took to mean that, yeah, you can kind of pan the camera around, but probably not the same control as the VO. It just seems to me that there's a certain level of world knowledge in VO as well, right? Because it has gravity and walking and cars and stuff like that. So there's some redundancy between the two, but fundamentally they're a little bit more focused. One creating videos, one creating video games, kind of.
Yeah, my guess is that in VO you might be able to create unrealistic things more easily, right? So
Possibly.
if you wanted a kid to be riding a horse and it transforms into a motorcycle, I don't know if Genie can do that.
Yeah, probably. I mean, Genie can follow the initial. One of the things I think they said is the earlier, like Genie 2, you had to start with an image. Genie 3, you can start with a prompt, which doesn't seem like a huge jump because in Genie 2, you could have used something else to take prompt to image and then feed the image into the initial latent state. But yeah, I think you are right that these prompts along the way, you might be able to say prompt, turn the robot into a horse. And it might be able to guide it that way.
Yeah, I mean, I'm just trying to think that maybe wasn't unrealistic enough, but you know, like a piñata that the kid hits and it explodes like a volcano, but instead of lava, it's daisies, and after half a second, the daisies do something completely not in our physics. You know what I mean?
Yeah.
They launch like rockets. Like I don't know, but
We'd
I'm just
have to
guessing
play with
that
it,
all
but
the effort on this world thing means that Genie maybe knows a lot more about physics. But if what you want is something that totally defies physics, then how does that help?
perhaps. The other really big difference is that where Genie is focusing on this consistency over minutes now, where I guess VO, I don't know what the most recent version of VO is, but it's shorter clips, right? So that's
I still
one
haven't been
difference.
able to do more than 8 seconds with VO3. That's the latest one.
Okay. And the other thing is that, so there was one of them watched, one of the videos was with the developers, and they went through, and they basically made it very clear that this is just a research kind of preview. there isn't a product. There's nothing that you're not gonna go out and find be able to play with it. They're just showing you what it can do. Presumably, I don't know if this is kind of the way, Jerry, you might know, is this the way Google rolls things out? I don't know. But it's just a preview at this point.
Yeah, preview is common, but the fact that you can't play with it is kind of, well, I guess that's VO you could always play with.
Mm-hmm.
It got better and things like that, but even from the get-go, you could make your abominable snowman run and go eat a donkey or something like that, right? Early on in the game.
Be really expensive. Maybe it's really expensive.
Yeah, that you could very well be right, Julius. I mean, creating the environment, getting all the physics right, and whatever the cycles they have to burn to do that could be a pricey product.
Yeah, for VO, I know at least when you generate VO3 on Google Cloud, it's super pricey. So if it's anything like that, it's probably.
Yeah. Well, they give you a cheap one, right? A for free one type thing. But yeah, if you want to do anything serious, you're going to be spending some money.
Well, yeah, I think I think they only have one, or maybe I don't know exactly. I just remember for using VO3 specific, like you can use VO2 if you want, and that's cheap, but VO3 specifically is like
right.
Everything.
But then
at $20 a month, I can do 3 per day. On VO3.
Yeah. But yeah, all of them are expensive though. All the VO level products are expensive.
So most of this, like I said, shows like a kind of a product demo. It's good, high quality image and pretty smooth and interactive. I can see where it could become, kind of a cool video game, but it depends on how much compute. How big of a PlayStation do I need to run this?
Well, it's not the PlayStation. It's it's that huge cluster behind it that's actually generating the bits.
That's doing it all for me. Yeah, that's dedicated to my video game.
Yeah, and your fiber optic link to it.
Right.
Yeah, I wonder, Roger, have you seen anything when they say it can do it in real time? Using what kind of computer?
No. So yes on the real time, no on the what does it take to do it. They just said you can do it.
Like, is it a single GPU? Is it just a single 8-node H100 cluster? Or is it like,
So there was this one source that I found, this the Genie 3 AI model complete technical guide, but I don't know how much credence to give to it. And they said that they thought that inference might be, see if I can find it, something that like you could run on, 4 high-end NVIDIA H100. So a video, a console with 4 H100s might achieve it. I said, I don't.
It says they use 8 TPU V5s.
Yeah, for single instance.
If you optimize it, then you might be able to get it down to 4 GPUs.
Yeah, it says let's see,
H100 GPUs. Again, I don't know how much credibility to assign to this article, but it was one place I did see that.
That to memory bandwidth over 2 terabytes per second. That might be a bottleneck.
By the way, along those lines, I was reading something talking about, these large data centers, for training and inference of models and stuff like that. And the CEO was referring to H100s as older technology. And I was just like, I haven't even used an H100, and you're already calling it older technology.
He's playing the game at a different level, Ted. I'm sorry to say.
Yeah, right. They signed a whatever $40 billion contract with OpenAI.
Right. You need to talk to your boss about freeing up some cash. I know he's,
Yeah.
So here
This
was
is
the
cool, Roger.
world
Yeah,
memory
this
summary
is really
again, where Gemini just says that it wasn't something special. It just kind of happened out of attention and latent state. And the one other thing I ran across that was kind of interesting during this was Sima, which a different part of DeepMind is creating AI models that interact with virtual worlds to control the virtual world. So Genie 3 is creating these virtual worlds that you can interact with, and they have another one that's that will interact with virtual worlds and decide what to do. And I think if I recall during this article, this video with the some of their developers, they did actually at one point plug the two together, which was kind of interesting. Well, anyhow, I think that was we're kind of on the time mark, and I think I'm pretty well through the slides. So
nice job,
so
Roger.
thanks. It was interesting. Like I said, it was a little disappointing not to. I was kind of hoping to get more technical details, but it's pretty interesting to see what the state of the art is. So
Yeah.
if
And
any,
they have a little more, horsepower than most of us have to run too.
yeah, yeah, exactly.
Okay, I'm going to stop the recording then. Is
Yeah,
that good?
unless there's any questions, let any questions come forth. If not, yeah, let's just stop the recording. Okay.
Okay.